Imagine a heavy block of steel, a raw piece of metal with no shape, no function, just a dense mass of material. And yet from that single block, it is possible to create the crankshaft of a car engine, a turbine component inside a jet aircraft, a surgical instrument, or a mechanical part that must operate with a precision smaller than the thickness of a human hair. How does a hard piece of metal turn into a perfectly shaped and extremely precise mechanical component? The answer lies in a manufacturing process known as metal machining. It is one of the most fundamental technologies in the entire industrial world. Instead of melting metal or casting it into a mold, machining removes material from a workpiece in a controlled way until the desired shape and dimensions are achieved. If you like similar educational content, please like, subscribe, and share the video with your friends. The basic principle is surprisingly simple. A cutting tool moves relative to the workpiece and removes a thin layer of material. The removed material forms what are called chips. But behind this simple idea lies a complex physical process involving enormous forces, friction, heat generation, and microscopic changes inside the structure of the metal. When the cutting edge of a tool enters the surface of the metal, the material does not simply split apart. First, it undergoes intense plastic deformation. The crystal structure of the metal is compressed and distorted. Atoms shift relative to each other, and only after this deformation does a thin layer of material separate from the surface in the form of a chip. In the small region where the cutting tool meets the metal, enormous pressure is generated. Temperatures in this cutting zone can reach several hundred degrees Celsius and sometimes exceed 1,000 degrees. Despite this, the entire workpiece does not heat up to such extreme temperatures because a large portion of the heat is carried away by the chips themselves. For this reason, machining processes often use cutting fluids. These fluids serve several important functions. They cool the cutting zone, reduce friction between the tool and the metal, and help remove chips from the area where machining takes place. There are several fundamental machining operations used throughout industry. The most common include turning, milling, drilling, and grinding. In turning operations, the workpiece rotates while the cutting tool moves along its surface. This method is ideal for producing cylindrical shapes such as shafts, rings, or threaded components. In milling, the situation is reversed. The cutting tool rotates at high speed while the workpiece moves in controlled directions. Milling allows the creation of flat surfaces, slots, pockets, and complex three-dimensional geometries. These machining processes make it possible to produce mechanical parts with remarkable precision. Modern manufacturing often requires tolerances measured in micrometers, meaning dimensions smaller than a human hair, which typically measures around 70 micrometers in diameter. But this raises an important question. How can a cutting tool survive the enormous pressure and temperature involved in machining metal? Why do some materials produce long spiral chips while others break into small fragments? And how do engineers control the speed, feed, and depth of cut to achieve both efficiency and precision? To truly understand metal machining, we need to look closely at the tiny region where the cutting tool meets the metal surface. This area, often only a fraction of a millimeter wide, is where one of the most intense mechanical processes in modern manufacturing takes place. When the cutting edge of a tool penetrates the material, the metal does not simply split apart like wood under a saw. Instead, it first undergoes severe plastic deformation. The material is compressed and forced to flow along a specific plane known as the shear plane. Along this shear plane, the internal structure of the metal rapidly rearranges. Atoms slide relative to one another under enormous pressure, and eventually, a thin layer of material separates from the workpiece. This separated layer becomes a chip. The formation of chips is a defining feature of machining. The shape of these chips provides valuable information about the cutting conditions and the material being machined. In softer and more ductile materials, such as aluminum or mild steel, the chips often form long, continuous spirals. These ribbon-like chips can sometimes become tangled around the cutting tool if they are not properly controlled. In contrast, brittle materials such as cast iron tend to produce short, fragmented chips. Instead of forming long spirals, the material breaks into small pieces as it fractures under stress. The type of chip formation depends on several factors, including the material's microstructure, the geometry of the cutting tool, and the cutting parameters used during machining. At the same time, enormous forces act on the cutting edge of the tool. The pressure in the cutting zone can reach several gigapascals. To put that into perspective, this is far greater than the pressure inside a car tire or even many hydraulic systems. Such extreme pressure combined with friction generates significant heat. In many machining operations, temperatures in the cutting zone range between 500 and over 1,000 degrees Celsius. However, the workpiece itself usually does not reach these temperatures because a large portion of the heat is carried away by the chips as they leave the cutting zone. To control temperature and friction, cutting fluids are frequently used. These fluids cool the tool and workpiece, reduce friction between the cutting edge and the metal surface, and assist in removing chips from the machining area. Another critical factor is the material of the cutting tool itself. Ordinary steel would wear out almost immediately under such extreme conditions. For this reason, modern cutting tools are made from advanced materials designed to withstand high temperature, pressure, and abrasion. The most commonly used tool material is cemented carbide. This material is made by combining extremely hard tungsten carbide particles with a metallic binder. The result is a tool that is much harder and more heat-resistant than conventional steel. In more demanding applications, tools made from ceramic materials or cubic boron nitride are used. Cubic boron nitride is one of the hardest known materials and is particularly effective when machining hardened steels. In addition to tool materials, machining performance depends heavily on three fundamental cutting parameters: cutting speed, feed rate, and depth of cut. Cutting speed determines how fast the cutting edge moves relative to the surface of the material. Feed rate controls how quickly the tool advances across the workpiece. Depth of cut determines how much material is removed in a single pass. Together, these parameters define the efficiency of the process, the surface quality of the part, and the lifetime of the cutting tool. Now that we understand what happens in the cutting zone, the next question is how machines control the process with such extraordinary accuracy. The answer lies in the machines themselves and the way their movements are controlled. One of the most traditional machining tools is the lathe. In a lathe, the workpiece rotates at high speed while the cutting tool moves along its surface. Because the material spins around a central axis, this method is ideal for producing cylindrical shapes such as shafts, rings, bushings, and threaded components. The cutting tool on a lathe gradually removes thin layers of metal while moving either parallel or perpendicular to the axis of rotation. With careful control, this process can produce extremely smooth and precise surfaces. Another major machining process is milling. Unlike turning, where the workpiece rotates, milling uses a rotating cutting tool called a milling cutter. The tool spins at high speed while the workpiece moves underneath it in carefully controlled directions. This method allows the creation of flat surfaces, slots, pockets, gear teeth, and complex three-dimensional shapes. Milling is one of the most versatile machining processes and is used to manufacture a wide variety of mechanical components. In the past, these machines were operated manually by skilled machinists who controlled the movement of the tool using mechanical hand wheels. While this method allowed great craftsmanship, it limited both speed and repeatability. Modern manufacturing relies primarily on CNC machines, which stands for computer numerical control. In CNC machining, the movement of the machine is controlled by a computer program. Instead of manually guiding the tool, engineers create digital instructions that define every movement of the machine with extremely high precision. These instructions tell the machine exactly where the cutting tool should move, how fast it should travel, how deep it should cut, and when each operation should begin or stop. Most CNC machines move along three main axes, X, Y, and Z. These axes correspond to movement in three perpendicular directions. However, many modern machining centers include additional rotational axes, creating what are known as five-axis machining systems. 5-axis machines allow the cutting tool to approach the workpiece from multiple angles without needing to reposition the part. This dramatically increases efficiency and enables the production of extremely complex shapes, such as turbine blades used in aircraft engines. Precision in machining depends not only on the computer control, but also on the mechanical design of the machine itself. The frame of the machine must be extremely rigid to prevent vibration. High-precision bearings and linear guides ensure smooth motion. Temperature stability is also critical because metal structures expand slightly as temperature changes. Even a tiny thermal expansion can affect precision. That is why high-end machining centers often include sensors that monitor temperature and automatically compensate for thermal expansion during operation. Modern CNC machines can achieve dimensional accuracy within a few micrometers. To understand how precise that is, consider that a typical human hair has a diameter of about 70 micrometers. After machining is completed, parts are often inspected using coordinate measuring machines, commonly called CMM systems. These devices measure the geometry of a part with extreme precision and verify that it meets the required tolerances. Through the combination of advanced machine design, computer control, and precise measurement, modern machining systems are capable of producing components with remarkable accuracy and consistency. Modern metal machining is no longer just a mechanical process performed by a single operator standing next to a machine. Today, it is part of highly automated manufacturing systems where computers, robots, sensors, and advanced software work together to produce complex parts with incredible speed and precision. In many modern factories, machining centers operate as part of automated production cells. Industrial robots load raw metal parts into CNC machines, remove finished components, and place them onto conveyors or into measurement stations. These robotic systems allow production lines to run continuously, sometimes 24 hours a day, with minimal human intervention. This type of manufacturing environment is often referred to as a flexible manufacturing system. It allows different parts to be produced on the same set of machines simply by changing the digital machining program. Instead of rebuilding an entire production line, manufacturers only need to update the software controlling the machines. Another major challenge in modern machining is the increasing use of advanced materials. Industries such as aerospace, energy, and medical engineering rely heavily on materials like titanium alloys, hardened steels, and nickel-based superalloys. These materials are extremely strong and resistant to heat, which makes them ideal for demanding environments. However, these same properties also make them difficult to machine. They tend to generate very high temperatures during cutting and can quickly wear down even the hardest tools. To solve this problem, modern cutting tools are often coated with extremely thin layers of advanced materials. Coatings such as titanium nitride or aluminum titanium nitride significantly improve wear resistance, reduce friction, and allow the cutting tool to withstand much higher temperatures. Another important development in machining technology is the use of digital simulation. Before any real metal is cut, engineers often simulate the entire machining process using specialized software. The simulation checks tool paths, predicts cutting forces, and ensures that the tool will not collide with the workpiece or machine components. This allows engineers to optimize the machining strategy before production even begins, saving time, reducing tool wear, and minimizing the risk of costly errors.